Hello and welcome to the Big Bang Theory and the Evolution of Our Universe, Lecture 2 in my 6-part lecture series, Cosmology, the Study of the Universe. My name is Fulvia Fiorani. In this lecture, we take a look at the evolution of our universe over the past nearly 14 billion years. The Big Bang Theory is our current cosmological theory that describes the evolution of our universe. We will see how the universe emerges from an initial extremely hot and dense state and evolves through expansion and the action of gravity to form the first stars, galaxies, clusters of galaxies, and the cosmic web we see today. Along the way, we will also explore the possible future of our universe. If you're a fan of the TV show The Big Bang Theory, you'll probably remember the theme song starts with "Our whole universe was in a hot, dense state. Then nearly 14 billion years ago, expansion started. Wait." And then the song goes on and ends with "Math, science, history, unraveling the mystery that all started with the Big Bang." Throughout this lecture, we will see how true this theme song really is. Okay, so aside from a little humor, let's take a look at what we will cover today. We start with an overall picture of the Big Bang Theory and how it was developed. We will see that the fundamental observation of modern cosmology is that the universe is expanding, and from that we can determine the age of the universe. We will see how the universe evolves in time through the formation of the first stars, then galaxies, clusters, and superclusters of galaxies, and finally filaments, voids, and the cosmic web. This is all known as structure formation. We will then talk about a refinement to the standard Big Bang model called inflation. And throughout the lecture, we'll get a preview of dark matter and dark energy and its role in the evolution of our universe. And finally, we'll talk about the possible future fate of our universe. So let's begin with what the Big Bang Theory is. The Big Bang Theory is the theory that describes the expansion and evolution of the universe from an initial extremely hot and dense state, 13.8 billion years ago, to the cold and sparsely populated universe of stars and galaxies we see today. What the Big Bang Theory does not describe is the bang itself. In other words, it does not describe what happens at exactly t equals 0. But it does describe what happens just fractions of a second after that. So how did this theory come about? It all starts with Einstein's general theory of relativity, published in 1915. General relativity is in essence a geometric theory of gravitation, and it describes large-scale physical phenomena and the structure of the universe. Perhaps Einstein's greatest insight is that space-time can actually change or curve. In other words, space-time is not fixed. The curvature of space-time is determined by the presence of matter and energy. The relation between matter and energy and the curvature of space is specified by what are called Einstein's field equations. In 1922, the Russian mathematician Alexander Friedmann found solutions to Einstein's equations that supported an expanding universe. It is important to remember that at this time, everyone believed in a static universe, including Einstein. And not only did his solution support an expanding universe, but he realized that he was dealing with a family of solutions, each describing the universe with a different shape or a different geometry. Another extremely important suggestion his solutions were telling him is that the redshifts of certain objects, indicating that they were moving away from us, was not caused by the objects moving through space, but it was caused by space itself stretching or expanding. We will cover this concept in a couple more slides. It is somewhat of a mystery why Friedmann's work was initially ignored, maybe because everyone believed in a static universe, and there was no observational proof otherwise. Or maybe as a pure mathematician, he was content with the mathematical solutions and not much interested in the physical applications. In any event, Friedman died at a very young age and was not able to support his findings. It was left to another person to solve the equations and apply them to probing the nature of the universe. That person was Father George Lemaitre, a Belgian Catholic priest and theoretical physicist. Independently from Friedman, Lemaitre also found solutions to Einstein's equations that supported an expanding universe. And unlike anyone else before him, Lemaitre tackled the question of what those equations were telling him about the origin of the universe. Lemaitre reasoned that if in fact the universe is expanding, then it was smaller yesterday than it is today. So if the universe is smaller and smaller as we go back in time, it is reasonable to think that at some finite point in time, the universe was concentrated into what he called a small primeval atom, which then exploded outward, breaking up into fragments that became atoms, stars, and galaxies we see today. Now, although his original model has been considerably modified, his idea that the universe had an origin and expanded into what we see today is at the heart of the Big Bang theory. So he is rightly considered the father of the Big Bang. Now let's go back to Einstein for a moment. Before Friedman and Lemaitre, Einstein realized that his equations could lead to an unstable universe, or in other words, a dynamic universe. But Einstein firmly believed in a static universe like everyone else did at the time. Specifically, his equations showed a gravitationally collapsing universe. So he added a term to his equations called the cosmological constant, a mysterious force of empty space that would push outward and balance the inward gravitational collapse of the universe. He never liked this constant, but needed it to support a static universe. Once it was observationally discovered that the universe is not static, but that it is expanding, Einstein dispensed with the constant, calling it the biggest blunder of his life. We will see later that maybe it wasn't a blunder after all. The actual discovery that the universe is expanding was made by the American astronomer Edwin Hubble in 1929. He is rightly considered the greatest astronomer of the 20th century. His discovery was preceded by another important discovery he made in 1925, that the Milky Way is not the only galaxy in the universe. In fact, until then, the Milky Way was considered to be the entire universe. While studying the Andromeda Nebula, he identified a Cepheid variable star. Using Henrietta Leavitt's period luminosity relation, he was able to calculate the distance to the nebula. The distance was much farther away than the size of the Milky Way galaxy. Therefore, he concluded that Andromeda must be another galaxy that is outside of our Milky Way galaxy. Armed with this knowledge, Hubble and his assistant Milton Humason set out to study these distant objects in greater detail. Now, Humason has a very interesting background. He dropped out of school when he was 14 and eventually got a job as a janitor at the Mount Wilson Observatory. With each passing night, he learned more and more about what the astronomers were doing and about their photographic techniques. Within 3 years, he was appointed as a staff member in the photographic division, eventually becoming a fully fledged assistant astronomer and one of the world's finest astronomical photographers. Hubble took a liking to him and took him on as his assistant. Together, they set out to explore the redshift mystery that Vesto Slipher had observed when studying nebulae. Recall that redshift means that an object is moving away from us. Just like when a siren goes by, the pitch or its frequency decreases, so too the light from an object moving away from us gets stretched or its frequency decreases, and we see that as a redshift in its spectrum. So to study this, they divided their work. Hubble set out to measure the distance of these far away galaxies, and Humason would measure their redshift or their recessional velocities. So what do good scientists do when they've collected all their data? Well, of course, they plot their data to determine if there is a relation. In 1929, they had enough data to plot the recession velocity of each galaxy versus its distance. The plot shows a definite pattern, indicating that the farther away a galaxy is from us, the faster it is moving away from us. In 1931, they took even better data, as seen in this plot. The straight line indicates that the recessional speed of a galaxy is proportional to its distance. Their findings show that on a large scale, galaxies are moving away from each other, and that the faraway galaxies are moving away faster. What they discovered is that the universe is expanding. What we really mean by the universe is expanding is that it is space itself that is expanding. So it's not that galaxies are moving away from each other in some pre-existing space, but that it is the space itself that is expanding, carrying the galaxies with it. This is the fundamental observation in modern cosmology. The proportional relation between the velocity of a galaxy v and its distance d is known as Hubble's law. The constant of proportionality h0 is called the Hubble constant and is represented by the straight line in the plot. The Hubble constant describes the expansion of the universe. Specifically, it is the rate at which the universe is expanding at the present time. So if we accept an expanding universe, then as Lemaitre had suggested, the universe was smaller yesterday than it is today. So we can extrapolate back in time and come to the theoretical conclusion that at some finite time in the past, the whole universe was condensed into an extremely small, dense state from which it began to expand. We call that moment of first expansion the Big Bang. So the Big Bang is a moment in time, not a point in space. At that moment, all of space, time, matter, and energy were squeezed into a point of infinite density called a singularity. Our current laws of physics break down in a singularity, so we don't know what occurs at the moment of the Big Bang itself, but we do know what happens just fractions of a second later. We will talk much more about those very early conditions in the next lecture. So we know that the universe is expanding. However, without any observational proof of a temporal beginning, the expansion merely suggests that it may have started to expand at the Big Bang. In fact, there were other theories at the time, the most prominent one being the steady state model. And this also explained the expansion of the universe, but without a temporal beginning. We will not talk about this theory since it was proven wrong with the discovery of the cosmic microwave background. George Gamow was an early advocate of the Big Bang theory. In 1948, he was the first to put forth the idea of a hot Big Bang. He suggested that as we go farther and farther back in time, the universe gets not only smaller and smaller, but also denser and denser, and therefore hotter and hotter, so that the very early universe was in a very hot, dense state. As the universe expands, it cools down, allowing matter to form. Based on his and his collaborators' calculations, there should be a leftover remnant of that initial radiation, and that it should be detectable throughout the universe. Unfortunately, no one took him seriously at the time. Then in 1965, Penzias and Wilson, two radio astronomers who at the time were working for Bell Laboratories, accidentally made one of the greatest discoveries in cosmology. At the time of their discovery, they had no idea that they had discovered the remnant of the Big Bang, known today as the cosmic microwave background. The needed observational evidence to support the Big Bang had been discovered, therefore putting the Big Bang theory on firm footing and all other theories to rest. Penzias and Wilson were awarded the 1978 Nobel Prize for their discovery, even though at the time they had no idea what they had discovered. This is a map of the cosmic microwave background. We will talk more about it later, but for now this is a snapshot of the universe when it was only 380,000 years old. So now that we know the universe has a temporal beginning, we can then talk about its age. By measuring the expansion rate of the universe, both past and present, we can calculate how long the universe has been expanding since the Big Bang. So when we talk about the age of the universe, what we really mean is how long it has been expanding. If we know the current rate of expansion and know the expansion history by looking back in time, we can calculate the expansion time. So the expansion time is the age of the universe. This equation tells us that the expansion time t is equal to 1 over the Hubble constant, h0. Now, although this is a very simple equation, getting the correct value of h0 is not very simple. So what is the age of our universe? Well, the current calculations based on observations give an age of 13.8 billion plus or minus 20 million years. Now, before we leave this slide, I just want to mention something about the Hubble constant. Recall from an earlier slide that the Hubble constant is the rate of expansion of the universe. The value of h0 not only changes in time as the universe expands, but also as other cosmological parameters are improved, the value of h0 changes. Currently, there is a disagreement on its measured value. So depending on the outcome of these studies, we might see a change in the age of the universe. So now we know the universe started its expansion 13.8 billion years ago in an event which we call the Big Bang, and it's been expanding ever since. So now let's take a look at how it has evolved to form stars and galaxies. We will talk about the first 380,000 years in the next lecture. Today we will start from the cosmic microwave background and through the dark ages to the formation of the first stars around 200 million years after the Big Bang, to the formation of the first galaxies around 400 million to a billion years after the Big Bang, and how galaxies have evolved over time and continue to evolve. Now, before we continue, we need to take a small diversion and ask ourselves, how do we travel so far back in time? Well, the answer is by seeing into the past. We can't travel into the past, but we can see into it. Most of the data astronomers work with is light. So what is light? Light is an electromagnetic wave. This is a simplified version of the EM spectrum. What our eyes detect is just a small portion called the visible or the optical light. At one end of the spectrum, we have the very high energy gamma rays. Then decreasing in energy, we have X-rays, ultraviolet, optical, then the low energy infrared, microwave, and finally radio waves. When we say that we detect light, what we mean is we detect electromagnetic radiation, some of which we can see with our eyes and some of which we cannot see. Now, as a wave, light from an object must travel through space to reach us, and therefore it must take time to reach us. Now, light travels through space at a speed of 186,000 miles a second. That is not a very intuitive number. We're not used to miles per second. So we really don't have a good feel for this number. In our familiar units, that comes out to 670 million miles per hour. So in 1 second, light goes around the Earth 7.5 times. Now, because astronomical distances are so large, astronomers use a unit of length called the light year, and that is the distance that light travels in 1 year, and that's about 6 trillion miles. Okay, so why did we go through all of this? Because the deeper we see in space, the farther back in time we see. Here are a few objects as an example. The sun is approximately 8 light minutes away, so we see the sun as it was 8 minutes ago. The Andromeda Galaxy is 2.5 million light years away. So since light has taken 2.5 million years to reach us, we see Andromeda as it was 2.5 million years ago. Galaxy cluster Abell 1689 is 2.2 billion light years away. So we see these galaxies as they were 2.2 billion years ago. So that's how we get information about the past, by seeing deeper and deeper into space. Okay, so how does structure, and by structure we mean stars, galaxies, clusters of galaxies, how does this structure form in our expanding universe? The basic idea in explaining how structure evolves is gravitational instability. The long-range force of gravity is the only known possibility to bring together material to form stars, galaxies, and large-scale structures. In essence, gravity is the architect of the universe. But for gravitational instability to work, there must be some initial small irregularities in the distribution of primordial matter. We see these irregularities as density fluctuations in the early universe. This is the map of the cosmic microwave background. Recall that this represents the conditions of the universe when it was only 380,000 years old. The density fluctuations appear as tiny temperature variations shown on the map by the different colors. These tiny variations are on the order of 1 part to 100,000. That means that in one area you might find 100,001 particles, and in another 99,999 particles. These very slight fluctuations are critical because they provide the seeds from which larger structures can grow and eventually collapse to form stars and galaxies. Cosmic structures build up hierarchically. So small structures collapse and merge to give rise to larger structures. So as the universe expands, gravity acts on the tiny density variations to form stars, galaxies, clusters, and superclusters, while the less dense areas become the voids between galaxies we see today. Now, before we talk about the formation of the first stars, we must briefly mention the role of dark matter in structure formation. Dark matter accounts for 85% of all the matter in the universe. We will see convincing evidence of this in our last lecture. Dark matter is the first type of matter to settle down in the early universe and forms filaments under the relentless pull of gravity. This image is the result of a computer simulation of dark matter filaments, along which the galaxies will later form as the ordinary matter falls into the gravity wells created by the dark matter. Dark matter, therefore, provides a framework onto which ordinary matter collapses to form stars and galaxies. Now, simulations show that without dark matter, there would not have been sufficient mass in the universe for structures to collapse and form stars and galaxies. So dark matter plays a very important role in the evolution of our universe. As we will see in our last lecture, dark matter has not been discovered yet, but there is overwhelming gravitational evidence to infer its existence. Now let's see an animation of what we mean by expansion causing clumps of matter to form and transforming a nearly smooth universe to form the first stars. In this animation, we will see as expansion occurs, gravity will act on extremely slight density variations to form clumps of matter. The areas with slightly higher density will pull more material together, forming clumps, whereas the less dense areas will become less dense and form voids. Initially, we will have both a global and a local expansion, but at some point, the clumps will slow down their expansion and start to collapse. So the animation will show as we go from a very smooth patch to a very rough patch with clumps and voids. So we start with a very smooth and expanding universe, and spread about are areas of slightly higher density. Initially, the expansion is both global and local. Even the denser regions expand, but the denser regions expand more slowly due to gravity. There comes a point when these denser regions stop expanding and fall back on themselves. So although the global expansion continues, locally the denser regions have collapsed. And it is within these regions that the first stars form. So I hope this very simple animation gives you an idea of what we mean by gravity forming structure as the universe expands. So let's take a look at the formation of the first stars and later the formation of galaxies. The first stars started to form about 200 million years after the Big Bang. Initially, the universe was very hot, and as it expanded, it cooled down, allowing primordial hydrogen and helium to form. Shortly after this, the universe enters a period called the Dark Ages. During this time, the universe is filled with an expanding gas, and as we saw in the previous animation, the higher density regions expand slower, eventually stopping their expansion and collapsing in on themselves. As the gas collapses, it gets denser and denser and hotter until it reaches the temperature at which nuclear fusion occurs, fusing hydrogen into helium, and a star is born. The first stars bring the first visible light to the universe, and therefore bring an end to the Dark Ages. The universe's Dark Ages simply refers to the absence of starlight. Now, we have not yet observed these first stars because their light is too redshifted for the Hubble Space Telescope. But there is great hope for Hubble's successor, the James Webb Space Telescope. So what were these first stars like? The first generation stars are called population 3 stars. They were made of primordial hydrogen and helium, produced shortly after the Big Bang. Today's stars, like our Sun, contain about 2% heavier elements as well. Because they were made of pure hydrogen and helium, the first stars were very massive, perhaps a few hundred times more massive than our Sun. Since they were so massive, they were also incredibly powerful. These massive stars would have lived very short lives, around 1 million years, and died violently as giant supernova explosions, seeding the universe with the heavy elements from which the next generation of stars and the first planetary systems would form. We will see element formation and the explosive process in more detail in Lecture 5. This is an artist's impression of what it may have looked like when the first stars burst onto the scene. In this impression, we see knots of blue-white, hot, newborn stars embedded in primordial galaxies. Of course, this is just an artist's rendering, but it is based on analysis of carefully extrapolating data back in time. This impression is also a perfect segue into our next topic, the formation of galaxies. From this point on, the theme of the universe is the growth of even larger structures in a hierarchical process, meaning that small things gather to make bigger things, which in turn gather together to make even bigger things. Around 400 to 600 million years after the Big Bang, the first groups of stars gathered to form the first galaxy building blocks. This is an artist's impression of these very early groups of stars, but they are actually visible to us in Hubble's deepest images. We'll see that in a few slides. These early irregularly shaped galaxies will eventually collide and merge and evolve into the familiar galaxies we see today. Now, let's not forget about dark matter. Recall that dark matter provides a gravity well for visible matter to fall into. So when we look at a galaxy, what we are seeing is the visible or the ordinary matter that has clumped into the center of a massive dark matter halo. As the hierarchical process continues, galaxies will gather into groups, clusters, and superclusters of galaxies, as we will see in a few more slides. Our Milky Way galaxy is a part of the local group, which is a part of the Virgo supercluster, which may be a part of an even larger structure called the Laniakea supercluster. However, recent studies suggest that Laniakea is not gravitationally bound. So what do our galaxies look like today? Most galaxies fall into one of two main types. This is a beautiful example of a spiral galaxy. These are beautiful galaxies with spiraling arms of newly forming stars. The arms rotate around the central bulge of generally older stars. This is an example of an elliptical galaxy. These are actually somewhat visually boring galaxies, as they show very little structure and do not have bright star-forming regions. Elliptical galaxies are primarily made up of older stars and look the same when viewed from different angles. Many elliptical galaxies are believed to form from galaxy collisions and mergers. We also have dwarf and irregular galaxies. Generally, these are much smaller galaxies, about 1/100th the size of the Milky Way, and they have irregular shapes that cannot be classified as either spiral or elliptical. Here are two examples. The Large Magellanic Cloud is a dwarf companion galaxy of our own Milky Way galaxy. We will see some beautiful images of galaxies taken by the Hubble Space Telescope in a few slides, but for now let's take a brief look at our own Milky Way as an example of a spiral galaxy. This is a beautiful view of our galaxy as seen from Earth in the southern hemisphere. It appears as a band of light that stretches across the sky. Its name comes to us from the ancient Greeks and Romans. The Greeks called it the Galaxias Kyklos, which translates to Milky Circle, and the Romans called it the Via Lactea, which translates to Milky Way. Now, before Edwin Hubble's discovery of other galaxies only 95 years ago, it was thought that the Milky Way galaxy was the entire universe. This, of course, is not an image of the Milky Way. Since we are inside the galaxy, we cannot get a view from the outside. So the next best thing is to use the image of a similar galaxy. Now, as mentioned, the Milky Way is a spiral galaxy. Spiral galaxies have a bright center bulge consisting of older, cooler stars, and the main characteristics of a spiral galaxy is its beautiful spiraling arms. These are long patterns of stars, gas, and dust spiraling out from and rotating around the center. New star formation occurs in the arms, seen here in blue indicating hot, young stars. The diameter of our Milky Way is about 150,000 light years across. Remember, 1 light year is 6 trillion miles. It has about 200 to 400 billion stars. It's difficult to get an accurate figure because it's very difficult to detect and count the number of very low mass stars. Our sun is located in the Orion Arm, at a distance of approximately 26,000 light years from the center. Now, all spiral galaxies rotate about their centers, and the sun revolves around the center with a speed of 490 miles per hour. And at that speed, it takes the sun 240 million years to complete one revolution. This is an edge-on view of a spiral galaxy. From this view, we see that spirals have a very flat disc-like shape with a beautiful halo of stars surrounding the center bulge. The spiraling arms form the flat disk. The dark areas in the disk are the areas of dense interstellar gas and dust from which new stars are born. Once again, our Sun is about 26,000 light years from the center, and from our position, we obviously cannot see the galaxy from the outside. But we can look towards the center, and that's a pretty exciting view, so let's take a look. We take a look at the center region of the Milky Way through the eyes of NASA's three great space observatories. The first view is from the Hubble Space Telescope. This captures light in our visible range. Unfortunately, the very dense gas at the center blocks much of the visible light, so we need some help from the other two observatories. The second view is from the Spitzer Infrared Space Telescope. Spitzer captures the low-energy infrared light that penetrates through the dense gas. The third view is from the Chandra X-ray Telescope, and this captures the very high-energy light beyond our visible range. Now notice the brightest region in the Hubble's image, and we can see that both in the infrared and X-ray images, it corresponds to greater areas of low energy and high energy, respectively. Now keep your eye on that spot as we merge the three images together. This is the center of our galaxy. As you can see, all three images combine to give us a spectacular view of the galaxy's central region. The actual center is located in this very bright area. The area is called Sagittarius A. Now within Sagittarius A, there is another small but very strong radiation source called Sagittarius A star. And Sagittarius A star is our very own supermassive black hole. It turns out that most galaxies have supermassive black holes at their centers. We will talk more about these in Lecture 5. So now let's simply enjoy some beautiful images of various galaxies as seen by the Hubble Space Telescope. Our first one is Andromeda. Andromeda is a spiral galaxy and is our largest galactic neighbor at 2.5 million light years away. And before we leave Andromeda, I would like to point out that although on very large scales galaxies are moving away from each other, galaxies within a group or a cluster may be moving toward each other because of their mutual gravitational attraction, and may collide and even merge with each other, as is the case with our own Milky Way and Andromeda. But not to worry, their merger will not occur for another 4 billion years or so. This is the famous Pinwheel Galaxy. We can see young, hot blue stars forming in the beautiful spiraling arms. And here is the beautiful Sombrero Galaxy. This is an edge-on view of a spiral galaxy in which we can clearly see the central bulge surrounded by a halo of older stars. And once again, it is the spiraling arms that form the disk. This is a barred spiral galaxy. They are called such because the arms extend from a bar-like structure of stars that goes through the center. Our Milky Way is actually a barred spiral galaxy. And here's another gorgeous spiral galaxy with very obvious bluish clusters of young stars. And in this image, you can also see many galaxies in the background. The next 6 slides are of interacting galaxies. So galaxies are often clustered together. Sometimes they can interact with each other and eventually merge. This is the famous Whirlpool Galaxy with very well-defined spiraling arms. And it is thought that the interaction with the companion elliptical galaxy helps to form such prominent arms. These two galaxies will continue to swirl around each other, exchanging gas, dust, and stars until a few billion years they will become one galaxy. Now, as galaxies interact, gas and dust flows from one to the other, often distorting the galaxy and giving us some spectacular views. Here is a beautiful example of a pair of galaxies that are tidally distorted through their mutual gravitational attraction. And this pair of interacting galaxies is called the celestial bird for obvious reasons. And in it, we see a spiral galaxy being stretched by the interaction of an elliptical galaxy. Our last slide on interacting galaxies is the beautiful image of the Antennae galaxies. These two galaxies have gone beyond just interacting at a distance and are in the merging process. They are currently going through a starburst phase, in which the collision of clouds of gas and dust sparks rapid star formation. This gives us a peek into what the Milky Way Andromeda merger may look like in about 4 billion years. Now, we've just seen some beautiful images of galaxies, but galaxies are just building blocks of larger cosmic structures. So let's see how the universe continues to evolve through the process of large-scale structure formation. Large-scale structure refers to all structures bigger than individual galaxies. As mentioned before, gravity is the chief architect of the universe and is the primary mechanism for the growth of large structures in a hierarchical buildup process through gravitational instabilities. But for gravity to work, there needs to be some initial roughness. We find this initial roughness in the cosmic microwave background. Recall that these colors simply represent the tiny density fluctuations on the order of 1 part in 100,000. Over time, these slightly denser and less dense regions will have grown into the large-scale structure we see today. Next, we will see a simulation of large-scale structure formation from the very early and smooth universe to the clumpy universe of galaxies we see today. We will see that over time, the denser regions get denser and the less dense regions get even less dense. And here's a quick simulation. So the brighter areas indicate where galaxies have clumped or clustered together. This map shows 250,000 galaxy positions out to about 2 billion light years. What we see is that galaxies are distributed neither uniformly nor randomly, but they tend to make up a patchy network, including large areas of very few galaxies, called voids, and regions with many more galaxies, called filaments. So gravity pulls together galaxies into groups and clusters. Clusters are now collapsing into loosely bound superclusters and filaments, separated by lower density voids. This entire hierarchy of structures is called the cosmic web. In the next few slides, we'll take a look at some beautiful galaxy clusters as seen by the Hubble Space Telescope. Our first cluster is Abell 2218. It is 2 billion light years away, so we are seeing what these galaxies looked like 2 billion years ago. Now notice how many galaxies are clustered around the brightest region. Also notice the stretching of light. We will come back to this later. This is the beautiful and famous Abell 1689. We will see this cluster again and again in the last lecture. It is 2.2 billion light years away. With the exception of 4 obvious foreground stars, every point of light we see is a galaxy. Now here too, notice the stretching of light around the central cluster. Here we go deeper into space and therefore farther back in time to 5 billion years ago. Abell 370 is one of the first galaxy clusters where this bending of light was observed. This phenomenon is called gravitational lensing. In other words, light coming from behind the cluster is bent around the cluster by its gravitational field. We will talk more about gravitational lensing in the lecture on dark matter and dark energy. But what gravitational lensing tells us is that there is light coming from behind this cluster. So how far back in time can we see? This is the image of the Hubble Ultra Deep Field. It may not seem too impressive at first glance, but the most distant object is 13.2 billion light years away. So we are seeing about 13 billion years into the past, only 600 to 800 million years after the Big Bang, when galaxies first started to form. The Hubble Ultra Deep Field was taken by aiming the Hubble Space Telescope at a tiny, dark patch of sky for 27 consecutive days. The tiny patch is the width of a dime held at 75 feet away. In ground-based telescope, that same patch of sky is largely empty. Everything we see in this image, with the exception of 4 foreground stars, is a galaxy, many of which are very young, meaning they formed when the universe was very young. There are 10,000 galaxies within the Hubble Ultra Deep Field, and extrapolating this to the entire observable universe gives us approximately 130 billion galaxies. That's absolutely amazing. Less than 100 years ago, we thought that our Milky Way galaxy was the entire universe. Now, the very distant galaxies are smaller and less symmetrical than the closer, older galaxies, showing the rapid evolution of galaxies in the first couple of billion years after the Big Bang. These are some close-up shots of the galaxies in the Hubble Ultra Deep Field, and they reveal a very dynamic galactic life. Almost every panel shows oddball-shaped galaxies that are interacting and merging. These are the galaxy building blocks of the larger galaxies that come to dominate the universe after a few billion years. We also see some older galaxies, like this beautifully formed spiral galaxy, which is only 1 billion light years away. This amazing zoo of galaxies shows us that galaxies do evolve in time. And here we see some of the galaxy building blocks. They're very difficult to see, so we tried to highlight them in these squares. So these are some of the most distant galaxies ever observed. They are approximately 13 billion light years away, so we see them as they were less than 1 billion years after the Big Bang. They are 100 to 1,000 times smaller than our Milky Way galaxy. And some of them appear stretched into tadpole-like shapes, indicating that they are interacting and merging to form larger structures. So far, we have a very successful and beautiful theory that explains the broad expansion and evolution of the universe. But there are a few unexplained problems that the standard Big Bang model is not able to adequately explain. So we will briefly cover 2 of the problems. The first is called the flatness problem. The problem can be summarized as the universe is nearly flat today and was even more so in the past. Our best observations today indicate that on extremely large scales, the universe is geometrically flat. Now, that is not the problem itself. But what do we mean by a flat universe? From Einstein's general relativity, we know that the spatial curvature of the universe is related to its mass energy density. Now, there is a critical density for which the curvature of the universe is 0. And our observations today indicate that the mass energy density is very close to the critical density. So the problem is, for this to be, the conditions in the very early universe had to have been extremely fine-tuned, because any small deviation from a perfect balance would be magnified over time and would lead to a present-day universe very different from what we see today. The next problem is the horizon problem, which can be summarized as the universe is nearly homogeneous and isotropic today and was even more so in the past. To understand this, let's start with what is known as the cosmological principle. On very large scales, the universe is homogeneous, meaning the universe looks the same from wherever you look. In other words, there is no preferred location. And it is isotropic, meaning it looks the same in whatever direction you look. So there is no preferred direction. Now, the horizon problem refers to communication between different regions of the universe. How does radiation coming from one point in the sky, 13.8 billion light years away, know to be at the same temperature as the radiation coming from the opposite part of the sky, that is 13.8 billion light years away, in the other direction? We see this in the cosmic microwave background, where the light seen from all parts of the sky is to a very great accuracy at the same temperature of approximately 3 Kelvin, or very close to absolute zero. But how could regions on opposite sides of the observable universe be in thermal equilibrium if they are so far apart that due to the limited speed of light, they should never have been in contact with each other? An answer to these problems was proposed by the American physicist Alan Guth in a theory called cosmic inflation, or simply inflation. Guth suggested that just a fraction of a second after the Big Bang, the universe underwent a period of extremely rapid exponential expansion. After this extremely brief inflationary period, the universe resumed its evolution according to the standard Big Bang model. So how does inflation solve the previously mentioned problems? Well, inflation flattens out any initial curvature. The universe so rapidly expands that our observable portion of the universe appears flat. For example, imagine rapidly expanding the surface of a balloon to the size of the sun. Then its surface would appear flat to us. And for the horizon problem, Guth argued that a small patch of the universe that was small enough to achieve thermal equilibrium before inflation could then expand with inflation so that the microwaves coming from opposite sides of the sky today can be at the same temperature because they were once in equilibrium. Interestingly, it is thought that inflation also provides the mechanism for the generation of primordial density fluctuations. This theory suggests that inflation caused quantum fluctuations to be stretched out to microscopic scales. Now, before we leave inflation, I would like to emphasize two things. The first is that although most cosmologists believe in this inflationary period, inflation itself has not yet been observationally proven. And the second thing is that inflation is not a new cosmological theory. It merely extends and refines the Big Bang theory to include a very brief inflationary period of exponential expansion during the first moments of the universe's existence. Now, one of the most exciting discoveries in cosmology today is the discovery that the expansion of the universe is accelerating. This is just a preview. We'll talk much more about this in the last lecture. Now, every bit of matter in the universe exerts a gravitational pull on every other bit of matter. And so this creates a drag that should slow down the expansion of the universe. In the late 1990s, two separate teams of astronomers set out to measure the rate at which the expansion has been slowing down in the past few billion years. In other words, they wanted to compare the current rate of expansion with the past rate of expansion. But amazingly, both teams came up with the same shocking and unexpected conclusion that the current rate of expansion is accelerating, not slowing down. But what could cause such an acceleration? Well, we call dark energy that which propels the accelerated expansion of the universe. We don't actually know what it is, but we do know that it is a property of space itself that is in essence pushing things apart. Dark energy is so exciting because we know so little about it, and yet it makes up approximately 70% of our universe. Now remember Einstein's cosmological constant? He introduced a repulsive force that was a property of space to maintain a static universe. And then he called it his greatest blunder once the universe was proven to be expanding. Now, although he introduced it for the wrong reason, the cosmological constant is now the leading candidate for dark energy. So even when Einstein thought he was wrong, he was probably right. Now, let's put everything together and look at a timeline of the universe. So far, all of our observations indicate that the universe started to expand at a moment which we call the Big Bang, 13.8 billion years ago, when all matter, energy, space, and time were in one point called a cosmological singularity, and it has been expanding and evolving ever since. A tiny fraction of a second after the Big Bang, the universe underwent a very brief period of extremely rapid exponential expansion called inflation. In the period between inflation and 380,000 years after the Big Bang, the universe was basically a hot plasma. As the universe expanded and cooled, individual particles were able to combine and form nuclei, and eventually the first atoms of hydrogen and helium. This is when the universe becomes transparent for the first time, and we see this light today as the cosmic microwave background. Now, this very brief period will be the focus of our next lecture. The next period is called the Dark Ages. It's called dark because stars had not yet formed, so there was no starlight. During this period, the universe was basically an expanding cloud of hydrogen and helium, and gravity was starting its work of collapsing denser regions. Around 200 million years after the Big Bang, those denser regions finally collapse to form the first stars. As gravity continues its work, the first galaxies start to form around 1 billion years. The universe then continues to expand and evolve. Small primordial galaxies merge, and second and third generation stars and planetary systems form. Around 4.5 billion years ago, the universe's expansion started to accelerate, propelled by what we call dark energy. And here we are today in our accelerating universe. So where does it go from here? Well, let's take a look at the possible fate of our universe. We know that the universe is expanding, but gravity is also pulling together all the stuff in the universe. So there's somewhat of a struggle between the two. Now, when we say stuff in the universe, we are talking about a single entity called the mass energy density of the universe. Einstein's most famous equation tells us that all forms of energy and mass are interchangeable. Deep down, they are the same thing. A crucial point when it comes to the geometry of space is that they both generate gravity. So the fate of the universe depends on the total mass energy density of the universe. Cosmologists define a density parameter, omega, as the ratio of the average density of the universe to a critical value called the critical density. And here it is in equation format, where the critical density can be simply calculated, and it comes out to 5 hydrogen atoms per meter cubed. Okay, so how does the fate of the universe depend on its density? Well, if omega is greater than 1, or there's more stuff than the critical density, then the expansion slows down, eventually stops, and recollapses on itself. If omega is equal to 1, then there's just enough stuff so that the average density is equal to the critical density. Then the expansion slows down more and more and eventually stops at infinity. If omega is less than 1, then there is less stuff than the critical density, and the expansion continues to infinity. Maybe a picture will help. First, we look at the case before dark energy because it's a bit more intuitive. Our first case is for omega greater than 1, so the average density is greater than the critical density. And here we have the Big Bang. The universe expands to its present state and continues to slow down until it stops its expansion because there is so much stuff that gravity overcomes expansion. And the universe reverses its expansion and recollapses on itself. For omega equal to 1, the average density is equal to the critical density, and we see that the universe continues to expand but slows down more and more until it stops at infinity. For omega less than 1, there is less stuff than the critical value, so although the expansion slows down, it continues to expand to infinity. So now let's add dark energy. Here we have the previous possible fates that we've just seen, and here is a fourth geometry of the accelerating universe. So the fate of the universe seems to be tied to dark energy. So what is the future of our universe? Well, the real answer is we don't know. It seems to depend on the properties of dark energy, and we know so little about it. And that's what makes the study of dark energy so exciting. But let's take a look at some possibilities. Of course, we start with our current expanding universe, which we know is accelerating. If dark energy reverses itself at some point, then it is possible that the universe will recollapse on itself in what is known as the Big Crunch. If the acceleration remains constant, then the universe will continue to expand forever, getting colder and colder as galaxies drift farther and farther apart. And this is known as the Big Chill. If dark energy increases with time, it can eventually first tear galaxies, then stars, and finally atoms apart. This is known as the Big Rip. Once again, we really don't know which, if any, of these scenarios represents our future universe. At the moment, the answer seems to lie in the mysterious dark energy. But what we do know is that there is much more to the universe, and there are still great discoveries to be made. So let's summarize and see what we know so far about our universe. We live in an expanding and evolving universe that began in a hot Big Bang 13.8 billion years ago. We don't know about the bang itself, but we can go back to fractions of a second after the Big Bang and study the universe as it evolves. The Big Bang theory is our current cosmological theory that describes how the universe expanded from an initial extremely hot and dense state and evolved into the cold and sparsely populated universe of stars and galaxies we see today. The lambda cold dark matter model is our current model of Big Bang cosmology. It contains the cosmological constant lambda associated with dark energy and cold dark matter. It is the simplest model that provides a reasonable account for all of our observations. Over billions of years, gravity acts on primordial density fluctuations. Through a hierarchical process of collapses and mergers, matter moves towards high-density regions and away from low-density regions. This process forms the large-scale structures of galaxies, clusters, superclusters, filaments, and voids known as the cosmic web. So we have this beautiful theory that takes us from the earliest known periods of our universe to the large-scale structure we see today. So what's next? First, we have dark energy. So far, we know that it is propelling the accelerated expansion of the universe, but we know very little else. Then we have the exciting and recently discovered gravitational waves. This gives us a new tool to study the universe and the possibility of detecting non-light signals before the cosmic microwave background and therefore directly probing the very early universe. And lastly, there has been a very recent inconsistency between the key techniques for measuring the Hubble constant. Recall that the Hubble constant is the cosmological parameter that describes the expansion of the universe. It sets the scale, the size, and age of the universe. Could a resolution to this discrepancy bring about a fundamentally different model of our universe? Well, the jury is still out. As we conclude today's lecture, we come back to this amazing image of the Hubble Ultra Deep Field. And as we look 13 billion years back in time, we realize that we've learned so much about our universe in the past 100 years, and yet we still know so little. The next lecture in the series will explore our very early universe. We will see that the infant universe is a much different place than it is today, and that things happen very fast during this period. All of the fundamental particles that make up all of the ordinary matter and possibly dark matter in the universe were formed just fractions of a second after the Big Bang. And this image, as we've seen before, is a map of the oldest light in the universe and is a snapshot of our observable universe when it was only 380,000 years old. I hope you've enjoyed today's lecture on the Big Bang Theory and the evolution of the universe. Hope to see you next time, and thank you for watching.